Okay, so in this part, we are going to talk about material processes. It's a very important topic, and we need to know the material processes to understand how we could change yield strengths, ultimate strengths, how we could change surface hardening, and basically um, change different mechanical property of materials. So the outline of this session will be as follow. We will talk about iron carbon phase diagram, time temperature transformation curve or TTT curve, heat treatment, surface hardening, mechanical forming and hardening, cold and hot work. So iron carbon phase diagram, as you could see here, um, has two axes. The y-axis shows us the temperature and the x-axis shows us the carbon content of the iron. Okay, so here we have low carbon content between 0 almost to 2%, and we call it steel. When the carbon content increases in iron, we'll have a cast iron from 2% to 6.7%. So you could see some regions here, and the structure of iron changes when we move from one region to the other region. This iron carbon phase diagram is made based on quasi-static and slow changes of the temperature. We don't have a rapid change of temperature. We don't have the dynamic change of temperature. And basically we move vertically. Why? Because we know, for example, our metal has I don't know, let's say 1% of the carbon content. Yes, so the carbon content of our material is fixed, and now we are curious what happens if we change the temperature slowly. Let's say increase the temperature, and what happens to the structure? You see the structure of the material. Yes, so it changes. It changes from, for example, here we have perlite and cemented, yes, and it changes when we go above the critical temperature. Yes, when we go above that critical temperature, which is 727 degrees of Celsius, then the content, the structure of our material changes from perlite and cemented to austenite. So this is the austenite and cemented, and if we keep increasing the temperature, we'll go to the pure austenite. Yeah, so you see basically alpha is ferrite, gamma is austenite, delta is delta iron, Fe3C is cemented, and perlite is combination of ferrite and cemented. So these are names of iron structure. Yes, and we are not going to go deep into the differences of these structures, but what we know to understand is changes of the temperature could change the structure of the material, and finally could change mechanical property of the material. So the heat treatment could change mechanical property of the material significantly, and we should have this in our mind and consider it in our processes. Okay, so this diagram again is made based on slow and quasi-static change of temperature. There is another diagram, time temperature transformation curve or TTT diagram. Again, is based on iron, and you see that what happens in this diagram if it changes temperature quickly. So we have here one axis, the, the, the left axis, the vertical left axis is temperature. We have horizontal axis, which is time. Yeah, and we have transformation line. Okay, so we want to see what happens to the structure of iron if we get different passes on this diagram. Let's say we have iron at 800 degrees of Celsius, and we want to see what happens if it changes temperature at this specific, let's say, trajectory. Okay, so we are cooling down the iron, yes, on this specific pass, and we want to see what would be the final structure of our steel. So you see, if we basically reduce the temperature quite slowly, then we will end up with the pellet. Otherwise, we'll end up with cemented and bent. And if we basically decrease the temperature quite quick, then we'll have martensite. So we'll have MS, this is start of the martensite region, and this is MF, this is finishing of the martensite region. Yes, so here we'll have some martensite content, but if we keep decreasing the temperature, we'll have a pure martensite structure at the end. Here is the nose. Here is the nose of TTT diagram. Is the nose here. So if we avoid the noise, we'll end up having martensite. Otherwise, we'll have pellet, cemented, or bennett, or combination of these. So you see that we couldn't have martensite if we change temperature slowly, but we could have a different structure which is martensite and is much harder and let's say stronger than other structures of iron if it changes the temperature fast. Now we know why heat treatment is very important, and how heat treatment could change mechanical property of materials. We don't want to go into more detail, it's beyond the topic of our course, and that would be enough for us. Okay, now we want to name and categorize some important heat treatment processes. The first one is quenching. Medium or high carbon steel part is heated above a critical temperature, or 760 degrees of Celsius, allowed to equilibrate for some time. So we keep the temperature at above 760 degrees for some time, and then suddenly cool to room temperature by immersion in a water or oil bath. So now we know from the TTT diagram what happens. We'll have a martensite content, and that structure is basically very strong and hard. And now we want to see what is the stress strain diagram for that quench part. So that quench part, or the martensite part, will have higher yield strengths, so will have higher strengths, but it's hard and it's brittle. It doesn't have flexibility, it doesn't have softness, it doesn't have that plastic range, and just simply call it brittle material. Rapid cooling creates a supersaturated solution of iron and carbon called martensite, which is extremely hard and much stronger than the original soft material. Okay, don't confuse this hardness with surface hardness. When we say a material is hard, it means that it's brittle. The core and the surface both are hard and brittle. It doesn't have plastic range in stress strain diagram. And quenching makes the material brittle, and rapid cooling introduces strain to the part. Okay, now we are going to move to two other processes of heat treatment, annealing and tempering. Tempering, part can be reheated to a temperature 200 to 700 degrees of Celsius. Okay, not necessarily above the critical temperature, but we could go beyond that critical temperature as well. Then heat soaked and then allowed to cool slowly. Okay, so it's heat soaked. It means that it's in, let's say it's in the oven, the temperature is increased, the uniformly core and the surface all is reached to 700 degrees of Celsius, then we will cool it slowly. And that's the key difference between tempering and quenching. Results in the somewhat strength but stores some ductility. Okay, so the tempered material has a stronger mechanical property, has higher yield strength, has higher ultimate tensile strength, but it's less ductile. It means that the plastic range is shorter than the original material. Okay, so this is the original curve of the material, stress strain curve of the material. Okay, so it will be somewhat between the quench part and the original part, which we call that original part annealed part, and I will explain now why we call it annealed part. Okay, now what is annealing? Quenching and tempering process is reversible by annealing. Okay, that's a very nice, let's say, property of materials, that we could retrieve mechanical property, we could reverse the process by annealing. How we could do that? Part is heated above the critical temperature and allowed to cool slowly to room temperature. So very slowly, yes. So very, very slowly, quasi-static, yes. We will cool the part into room temperature. So the main difference between these heat processes is speed of cooling. Often used if no hardening has been done previously in order to eliminate any residual stress and strain. So I will explain coming slide how those residual stresses and strains happen because of some, let's say, cold working or hot working, um, or some other reasons. Those residual stresses and strains could accumulate into the part, and we want to release those. We want to retrieve the stress strain curve of the material, bring it back to the original shape, and may apply a new heat treatment. And it restores the original stress strain curve. So that's why I call it the original stress strain curve of material is the annealed one. So the annealed, let's say this is a low carbon steel. So the low carbon steel is ductile material, but if we apply the tempering or quenching heat treatment processes on that low carbon steel, then we will end up having a different strain. A stress strain curve will have a different yield strengths or ultimate strengths and different ductility and brittleness properties. Okay, surface hardening. So now you know that we have different scales for surface hardening. Yes. So by doing quenching, by doing tempering, the core and surface strengths and the brittleness changes. But we may want to keep the core property, mechanical property same, but changes only the surface property. How could we do that? One way would be by doing some chemical reaction. So only surface is hardened, leaving the core soft in surface hardening. What is the process? The processes are known as carburizing, nitriding, or cyaniding. Okay, so these are chemical processes. So these are not heat treatment processes. These processes will lead to a hard surface on a soft core and is referred to as case hardening. Okay, so the core will be in touch, but the surface will have a different mechanical property. Carburizing hits low carbon steel, so will increase the temperature in a carbon monoxide gas atmosphere, causing the surface to take up carbon in solution. So now surface has more carbon content than the core, and systems has more carbon content, so it will be more brittle, so it will be very similar, let's say, to the cast iron, not like a low carbon steel. Nitriding, very similar to the carburizing, hits low carbon steel in a nitrogen gas atmosphere and forms hard iron nitrides in the surface layers. And cyaniding hits the part in a cyanide salt bath at about 800 degrees of Celsius, and the low carbon steel takes up both the carbides and nitride from the salt. So cyaniding is combination of nitriding and carburizing because the surface will get both carbide and nitride. Yes, so we will have more carbon and nitrogen, let's say, content. Okay, other form of processing could be in a form of mechanical work. and we call it mechanical forming and hardening. One type of mechanical forming is cold working. What is cold working? Cold working takes the ductile material beyond the yield point and permanently deforms it. And we call it cold working because the temperature is not high and the temperature is a room temperature. So when we apply force and load and stress on a part, we already understood from stress strain curve that when it goes beyond the yield point, we'll have a permanent deformation and that will cause a higher yield strength. So mechanical property of the part could change by these type of processes. Mechanical working of metals at room temperature to change their shape or size will also call work harden and increase their strength at the expense of ductility. Reapplication of load puts the yield point Y at a higher stress and thus strain hardened the material. Okay, so here we have a stress strain curve. Let's say we have our annealed part, so we managed to retrieve the original shape of our stress strain curve of low carbon steel or ductile material. And now we apply stress. Okay, so we are applying a stress and going up of the curve and we are reaching to the point B. So we are beyond the yield point. So we could call it cold working. We are beyond that yield point and we are at point B. Okay, now we release the load, remove the load and stress. What happens to the curve? It won't back to the original original coordinates, the coordinate system point. It will back straight to the point A. Now the material has a new stress strain curve of ABF. If we apply the stress again, it will go up the curve from point A and will reach to the point B. You see that we'll have a higher yield strength. This is the original yield strength here, but the new material after cold working has higher yield strength at point B. It will be less ductile because the ductile region is much shorter than the original one, or we could call it basically more brittle, but it's stronger and the young module will remain the same. Okay, again, we could apply a new cold working process and go up the curve from point B and basically again reshape the part, go to the plastic region, reaches to the point C before fracture, of course, and then release the load. When you release the load, it will back to the point D. Now we are at point D, and DCF will be the new stress strain curve of the material after the second cold working process. You see now the material is very brittle. You have a very short range of ductility. We don't have that much plastic range remained, but it will have higher strengths, and the Young's module or stiffness constant will remain the same. As we said, we could retrieve the curve of a stress strain curve by annealing process, which was a kind of heat process. If we do the annealing, then the material will back to the original stress strain curve O, B, C, F, and we could apply other type of heat treatment processes, or we could apply some surface hardening processes or mechanical processes. Another type of mechanical process is hot working. If the material is mechanically worked above its recrystallization temperature, which is critical temperature of 760 degrees, it will tend to at least partially anneals itself as it cools. So what was annealing? Increasing temperature above that critical temperature and slowly decreasing temperature. Yes. So when we increase the temperature, it's hot working. Yes. So it's not a room temperature. The temperature of the part is already increased above that critical temperature. So while we are applying load, while we are applying stress, it will anneal itself. So that annealing process will release some stresses. Hot working reduces the strain hardening problem. Yes, so we had strain hardening issues with the cold working. We couldn't apply so much stress on a part, otherwise the part could break in cold working. But in hot working, because of that self-annealing, could reduce the strain hardening problem, but introduces its own problem of rapid oxidation of the surface due to high temperature. So we have a high temperature, it will absorb oxygen at the surface, and the surface will oxide. Hot rolled metals tend to have higher ductility, okay, while higher ductility because of the self-annealing. Lower strengths, again, because of that self-annealing. And poorer surface finish. Why poorer surface finish? Because of that oxidation. Than cold working metals of the same alloy. So why do we use hot working? Because hot working will gives us more of a range of plasticity. We could deform the part more before breaking the part. We have a variety of techniques for cold working and hot working. But just for an example, we'll present two videos for forging and extrusion. In this slide, you have forging, which basically we increase the temperature of the part. And see here we have this hydraulic press and the mold. And the mold will be pressed on to this part, and the part will get the shape of the mold. You see basically the vapors and carbons shows oxidation of part surface, and that's why we have poor quality of surface usually in hot working. Here we have extrusion, and in extrusion, billet of the extrudate is heated to a soft state. So it's heated, so that's why it is hot working, and then ramped at fairly high speed through the mold. Okay, so here we have basically it's the part is the preheated part, and here we have the press, the hydraulic press, which is going to ramp this billet into the mold. Okay, so here is the mold, and you see that now you have this profile of aluminium coming out of the mold. Okay, so here you could see the different profile of, let's say, aluminium could be made by extrusion. Another type of process is coating and surface treatment. And coating and surface treatment inhibiting corrosion and improving surface hardness and wear resistance. Also used to change dimensions, reflectance, color, and resistivity. So methods of coating, we have galvanic action, electroplating, electroless plating, plasma spray coating, anodizing, and chemical coating. Some of them might be familiar to you from physics or previous basically courses you had. Again, if you want to find the detail of each method, you could refer to the book. But that basically this list will serve the purpose for this specific course, and we are now going to the detail. So here in these pictures, you could see beads are coated. Here we have the diamond coated 2mm beads, and here we have thin coated drill bead. So the thin layer is sitting on this bead to increase the wearing and resistance property of the bead. So here the galvanic corrosion you see happen and the reaction happen between these bolts and nuts and the surface. So here in this picture you will see collapse of silver bridge happen because of rusting, and that's why we should have a coating and surface treatment. So this slide concludes the topic of mechanical property and processes, and from next week we'll move on to the next topic of static loads and deflections.